Hi students, I'm Kailash. In this online session today, I'll be teaching you Ohm's law in macroscopic form or macroscopic model of Ohm's law. Dear students, remember you don't have the statement in 12th standard Tamil Nadu Samachir book for both the microscopic form of Ohm's law as well as macroscopic form of Ohm's law. Statement is not there. So in earlier online class, we were dealing with, I taught you Ohm's law in microscopic form. So what is Ohm's law in microscopic form? Ohm's law in microscopic form states that at a constant temperature, the current density is directly proportional to applied electric field. So current density J is directly proportional to the applied electric field. So this is a statement of Ohm's law in microscopic form. Now when I put it in the form of an equation, I have J equals sigma into E, where sigma is a constant of proportionality called conductivity of the material of the conductor. And the conductivity sigma is equal to, here I have written the formula for conductivity. Sigma equals n E square tau divided by n, where n is number of free electrons present in unit volume of the conductor, E is the charge carried by an electron, tau is the average relaxation time, or it's the average time taken by an electron to undergo two successive collisions, and m happens to be mass of an electron. So this is your microscopic form of Ohm's law. Now today I am supposed to derive macroscopic form of Ohm's law. Now first let me tell the statement of Ohm's law. In fact, if they simply ask you Ohm's law, you have to write the statement given in macroscopic form, which is not there in Tamil Nadu Samachir 12th standard book. Please, you can make a note of it. So the statement, I will be telling you the statement, you can make the note of the statement. Okay, so Ohm's law in macroscopic form, or simply Ohm's law, states that at a constant temperature, the current flowing through the conductor, say I, is directly proportional to the potential difference applied between the two ends of the conductor. So Ohm's law in macroscopic form, or simply Ohm's law, if they simply ask you state Ohm's law, you have to write the statement in macroscopic model and not microscopic model. Please remember. Okay, so Ohm's law states that, or Ohm's law in macroscopic form states that the current flowing through a conductor is directly proportional to potential difference applied or potential difference across the two ends of the conductor. So to prove Ohm's law in macroscopic form, or to deal with Ohm's law in macroscopic form, my ultimate step has to be I is proportional to V. That is, I have to prove I is proportional to V. Current varies directly with the applied potential difference or voltage. So how to do that? It's very simple, nothing. Okay, now before proceeding to the derivation, in electrostatics, you would have studied the relationship between electric field and potential difference. So let me give a very small recap in it, because so that relation is required in this derivation. So let me give a small recap in it. Okay, you know electric field E is given by minus dV by dx. Let me write it here once again. The electric field is equal to minus dV divided by dx. Okay, now electric field is numerically equal to negative of potential gradient. Okay, let me analyze this quantitatively. Which means, let me omit the negative sign. dV means potential difference between 2 points. So here, let me consider a conductor PQ. The length of the conductor is L. Let the NP be connected to positive of the battery, and let the NQ be connected with the negative of the battery. So the battery is not shown in the diagram. So thus, between the two ends of the conductor, we are developing a potential difference, or we are applying a voltage. Let V be the voltage applied to the conductor, or let V be the potential difference between the 2 points P and Q. or between the two ends of the conductor. So once when the conductor is connected with the battery, an electric field will be established inside the conductor whose direction will always be from positive terminal to negative terminal or positive end to negative end. So an electric field E vector acts from positive end to negative end. So once when the battery is connected to the conductor or once when potential difference is applied, current will flow through the conductor, isn't it? So let I be the current flowing through the conductor. So you know the direction of current will always be from high potential to low potential, that is from positive to negative. So all these formalities you have to write, all these introduction part you have to write. So before starting the derivation. Right now, you know electric field E is equal to dV by dx. What is dV? Potential difference between 2 points. So dV, I am going to replace it with potential difference between the 2 points P and Q, which is nothing but V. So instead of dV, let me put V here. So V is the potential difference between the two ends of the conductor divided by distance between the two ends of the conductor is nothing but length of the conductor. So the dx is the distance between the 2 points between which the potential difference is dV. So here the potential difference V is the difference in potential between the 2 points P and Q, which are separated by a distance equal to L, which is nothing but length of the conductor, isn't it? So V divided by L. So electric field E can be expressed in terms of voltage like this. Potential difference between the ends of the conductor divided by length of the conductor. Is it clear? So you should remember this formula while dealing Ohm's law in macroscopic form. Okay, so E is equal to V by L. So never forget this formula. It's very important one, right? Okay. So we'll start the derivation. So to derive Ohm's law in macroscopic form, that is to prove current is directly proportional to voltage, I will be needing the help of Ohm's law, what we have dealt in microscopic form already. So you know Ohm's law in microscopic form states that current density is directly proportional to the applied electric field at a constant temperature. That is current density J equals to a constant sigma times electric field. So take this as expression number 1. So that sigma is already I have already I have discussed this, right? And sigma equals to n E square tau divided by n. Now what I am going to do is I am going to replace current density J with its formula and electric field, which is written in terms of voltage, so that particular formula. So I am going to replace J and E, or I am going to write J and E in terms of current and potential difference respectively. So how to do that? You know current density J is current per unit area, isn't it? So I divided by A. So take this as number 2. So just now we saw a relation between electric field and potential difference, isn't it? So electric field E is equal to potential difference between the two ends of the conductor, that is V, over distance between the two ends of the conductor, which is nothing but length of the conductor, L. So number 3. So I am going to substitute 2 and 3 in 1. So shall we do? Shall we substitute 2 and 3 in 1? We shall. So substituting 2 and 3 in 1. Okay. So instead of J, let me substitute I divided by A, I over A equals to, let me keep sigma as such. It's a constant, don't forget. And instead of E, let me substitute V by L. Okay, now what I am going to do is, I am going to rearrange this expression so that left hand side contains, or one side of this expression contains voltage alone, V alone, and all the other terms on the other side. Okay, so which means keeping V here as such, I will be rearranging, or I will be taking sigma and L to the other side, the left hand side. So on rearranging, I will be ending up with I. So L, when it goes to the left hand side, it goes to the numerator, divided by, when sigma goes to the left hand side, it goes to the denominator. So sigma A is equal to V. Okay, now let me rewrite it slightly in a different form. So V equals, Now, L by sigma A, I am just going to enclose this term within brackets and into I. So let me take it as number 4. So in the expression 4, within the brackets, we have a term L divided by sigma A. L is length of the conductor, which is a constant. As long as you don't replace the conductor, it's going to be the constant. And sigma is already a constant. It's conductivity, right? And A happens to be the area of cross section of the conductor. So as long as I don't change the thickness, as long as I don't change the conductor, right? So the thickness is not going to change, which means A is a constant. So the terms, whatever you see within the brackets, are absolutely constants. So in the next step, okay, let me rub this off. Let me just not consider this is equation number 4. Let me consider the next expression as 4. Okay, right? B equals, so L by sigma A is a constant. Since L is a constant, sigma is a constant, A is a constant, the ratio L to sigma A will be a constant. So let me replace L by sigma A by a single constant, a single letter R into I, where R is a constant, which is called resistance of the conductor. You know, resistance is the obstruction offered by the material for the flow of current, which is a constant. So R will be constant only when the temperature of the conductor will remain constant. So remember that, that's very important. So where R replaces the term L by sigma A, where R is called a constant, namely electrical resistance of the conductor. Okay, right. So R is equal to, let me take this as number 4. So next expression 4, R is equal to L divided by sigma A. So thus we can see the resistance of a conductor or material of a conductor depends upon number 1, length of the conductor, and number 2, cross-sectional area. So if the length of the conductor is more, then the resistance of the conductor will be more, and if the thickness of the conductor is more, that is, if the thickness of the conductor is more, then the area of cross-section will be more. The circle will be bigger if the thickness is more, right? So area of cross-section will be more. So if the area of cross-section is more, or in other words, if the thickness of the conductor is more, then the resistance of the conductor will be smaller. So the resistance of a conductor is directly proportional to length of the conductor and is inversely proportional to cross-sectional area for a given material. Suppose if I have 2 copper wires, the material is same copper. Since the material is same, both the copper wire will have the same conductivity. So that's what I mean by let us fix the material. So one copper wire is of length 2 meter. And the other one is of length 5 meter, and assume both of them are of same thickness and they have same temperature. So in this case, the copper wire of length 5 meter will have more resistance than the one to the length 2 meter. Okay, now let me consider 2 copper wires, one thin wire and the other one thick wire. Both of them are of same length and both of them are maintained at same temperature, imagine. And since both the wires are of same material, their conductivity will be same. Because conductivity, if you want to change conductivity, you have to change the material. So both the wires are of same material, so the sigma will be same. Right, now one wire is a thin wire of length 2 meter and the other one is of a thick wire of the same length 2 meter. Now among the 2 wires, the thick wire will have smaller resistance and the thin wire will have larger resistance. So thus, in expression 4, the term R is a constant which is equal to L divided by sigma A. Is it clear? So the resistance of a conductor depends upon number 1, length of the conductor, number 2, area of cross section of the conductor. Okay, now B is equal to R into I, isn't it? Right? Now what I am going to do is, I am going to remove the resistance from expression 4. I am going to remove the constant R from expression 4. So whenever you introduce a constant, proportional sign changes to equal sign. And whenever you remove the constant from an expression, the equal sign will change to proportional sign. Just a converse, right? So let me remove the constant R. So if I remove the constant R, then equal sign changes to proportional sign. Proportional sign, in fact. So V is proportional to I. But the thing is that voltage is independent factor and current is dependent factor. That means whenever there is voltage, there has to be current. Without voltage, no current. So whenever I say a current is flowing through a circuit or current is flowing through a conductor, we should have applied a voltage to the conductor. So unless you apply a voltage, no current flow is going to be there. So if you want a flow of current through a conductor, we need to apply a voltage, that is potential difference is necessary. So if there is potential difference, there will be flow of current, which means current flow depends on potential difference. That is, current is a dependent quantity and voltage is the independent quantity on comparison among themselves. So whenever I write an expression including a proportional sign, I have to write the dependent factor on the left hand side. That will be appropriate. So I is proportional to V. Because only when V changes, I will change. Only when V is there, I will exist. Okay, so I depends upon V. Okay, fine. Now in what way I is dependent on V? So I is directly proportional to V. So the current flowing through a conductor is directly proportional to potential difference between the two ends of the conductor at a constant temperature. So this is what we call it as Ohm's law in macroscopic form. Okay, so successfully we have derived Ohm's law in macroscopic form. I is proportional to V. Okay, now from expression 4. So after deriving this, you have to write the statement here. Ohm's law statement is not there in the book. At a constant temperature, the current flowing through a conductor is directly proportional to potential difference between the two ends of the conductor. You have to write that. Now after writing that, from expression 4, let me find what is R equals. So bring I to the left hand side. So V by I. So from expression 5, we can define resistance. So define resistance. Resistance is defined as the ratio of applied potential difference to the current flowing through the conductor. So resistance is defined as the ratio of potential difference between the two ends of the conductor to the current flowing through the conductor. Its unit has to be, unit of potential difference is volt and unit of current is ampere. So the unit of resistance has to be volt, ampere to the power minus 1. But we are not going to use it. Instead of volt, ampere power minus 1, we will be using the unit called ohm. So this is the symbol for ohm. So this letter is called omega. So the omega symbol, the omega Greek letter omega is used as a symbol for unit ohm. Okay, right. Now 1 ohm will be equal to 1 volt per ampere. Is it clear? So if a potential difference of 1 volt applied allows a current of 1 ampere or enables a current of 1 ampere to flow through a conductor, then the resistance of the conductor is said to be 1 divided by 1 is 1. So 1 ohm. So they may ask you to define 1 ohm. If they ask you to define 1 ohm, write the formula for resistance. R is equal to V by I. Now take all the values in the formula to be unity. So take potential difference as 1 and current as 1. So 1 by 1 is 1. You can define it very easily. So potential, whenever a potential difference of 1 volt applied to the two ends of the conductor enables a current flow of 1 ampere through the conductor, then the resistance offered by the conductor is said to be 1 ohm. So that's all about your macroscopic form of Ohm's law. And lastly, please use headphones for audio clarity. Okay, thank you. See you in the next class. Bye.